Okay, so hi everyone. Today we'll be talking about what do you say? Yeah, countable and uncountable sets. Like you know that there are finite sets, the sets which have finite number of elements, and then there are infinite sets which have infinite number of elements. But even in infinite sets, there are two different types of sets which are countable or uncountable. Like you would have probably seen some places in like some math textbooks that this is countably infinite, or this is uncountably infinite, but uh, it's likely that you wouldn't know what actually countably infinite or uncountably infinite means. So we'll talk about those sets today. There are only like 2 or 3 definitions which we'll do in first 5 minutes, and then the whole session is filled with like problems mostly. So it will be a chill session, and feel free to speak any of your ideas or anything, or if you have any doubt at any point. Okay, so we'll first start with injective function. So a function from set A to B is said to be injective if A and B are two sets, if f of x equals to f of y is true if and only if x equals to y, and this holds for all x comma y in A. This is the criteria for injectivity. And then there is a thing called surjectivity, which says for all y in B, there exists an x in A such that uh, f of x equals to y. And if a function is both injective plus surjective, it's called bijective. So are these three definitions clear? Okay, nice. So now let's see what a countable set is. Countable set. So suppose you have some set A, 1, 2, 7, anything. Then this set A is said to be countable if there exists an injective function f should be injective, which maps A to n. This is the definition of injective. Oh, sorry. This is the definition of countable set. And a set is uncountable if it's not injective. So like, what am I saying? Sorry. A set is uncountable if it's not countable. That's it. So if there is an injection from the set to the set of naturals, it's called countable, and otherwise it's uncountable. So I hope the definition is clear. Like it's not something fancy or anything. So like countable words suggest that you can count the sets. So basically, if there exists an injection from the set to naturals, so let's say you have the set of even numbers, which is 2, 4, 6, 8, 10, so on. And this is countable, right? Because you can map it into naturals. So like let's say we map 2 to 1, 4 to 2, 6 to 3. So like we map uh, f of x is equals to x by 2, 4, so on. So now you can count even numbers. So like you can say that which even number comes first, like 2 comes first, then 4 comes second, so on. So you're able to count them. So is it clear what is a countable set and what is an uncountable set? Okay, one person says yes. What about the other 3 people? I think they are. Okay, nice. So now let's do some questions. So like there are 4 one second, let me launch a poll. Okay, this is hard to manage on web. So these are 4 questions. If z is countable, z is a set of integers. If q is countable, q is set of rationals. And if n cross n is countable. So I assume people know Cartesian product. If they don't know, you can ask, then I can explain, and then you can mark your answer. and if your R is countable. So take 4 or 5 minutes and think whichever is countable or uncountable, and you can mark. I hope you people can see the poll, by the way. Hey, can someone just quickly tell if they can see the poll? Okay, thank you. Okay, instead of n cross n, you can also take z cross z here. It's basically the same idea. Uh, z cross z is basically, if you do not know Cartesian product, you can even think of it as that way. Set of all lattice points in R square. I hope people would know what this is. If you don't know, then I can explain. Just ask. Okay, one person is left to vote. Okay, everyone voted. So I'll share the result if you can see. Yeah. Okay. So everyone said that Z is countable. Can someone quickly tell me how this is countable? Any of you? Just unmute and speak.
You can take 0, then 1, -1, 2, -2, and so on.
Yes. So what you can do is like this looks something like -3, -2, -1, 0, 1, 2, 3, so on. So you can map this to 1, then you map this to 2, map this to 3, then you do 4, 5, and you can eventually map everything. So Z is countable. Okay, nice. Next, I asked if Q is countable, and okay, half people said it's countable, half said it's uncountable. So would anyone like to tell how they thought that if it's countable or uncountable? Like, don't worry if it's right or wrong, doesn't matter. Just present whatever you think. Like, if it's countable, then what's your map to naturals? And if it's uncountable, then why do you think it's uncountable? There's infinite number of rational numbers between any two discrete numbers, so it can't be counted. Hmm. Okay. Suppose Ashish, to answer your question, suppose I give you this set. S is the set of all numbers of the form 1 plus 1 by n, where n belongs to naturals. So what is this set? This is basically 2, then 1 plus 1 by 2, 1 plus 1 by 3, so on. And this contains infinite numbers between the interval 1 and 2, right? But you can count this. Like this seems countable, right? So you map 1 plus 1 by 1 to 1, 1 plus 1 by 2 to 2, 1 plus 1 by 3 to 3, and so on. You can count this. So like the point I'm trying to say is you are dealing with infinite sets only. Like uh, you're saying if an infinite set is countable or uncountable. So saying that two numbers have infinite numbers between them and it's uncountable is not really a strong argument. Like this is a counter example. So is it clear? Okay. To people who said it's countable, what's your injective map? I'll tell you it's countable. Now try to find a map from this to rational to naturals. Okay, one more thing I would like to add is this mirror is not good. Huh. So suppose you are mapping rationals into naturals, and suppose your map is something like, let's say you map some rational one, like your map would be f of 1, f of 2, then f of 1 by 2, something like that. And suppose in your map there is no x such that f of x is equals to 1. There does not exist an x. So that's fine because we're finding an injective map and not a surjective map. So you can basically skip a few naturals also. Uh, okay, that's probably not useful right now, but you can find clean enough maps if you don't care about skipping naturals. Okay, also everyone agreed that n cross n is countable. Can someone tell me a proof for that? How is that countable? Maybe that would help answering how q is countable easier. Okay, one sec. We can map xy to x star y. Eman, do you mean like, okay, sorry if I'm not pronouncing your name correct. Do you mean like we can map x by y to x times y? Oh wait, if you're answering for, okay. Oh, this doesn't work because we need an injective map, right? So you're saying that you map 1 by 3 to 1 cross 3, which is 3, and 3 by 1 to also 3. This is not injective, right? Because f of 1 by 3 is equals to f of 3, but 1 by 3 is not equals to 3. Okay, let's think of n cross n first. So what is n cross n? Basically, like if you consider this natural number line here and then here, you have 1 here, 2, 3, 4, 5, 6, so on. 1, 2, 3. And you have all these points basically. Like this intuitively feels countable, yes. Can someone tell me how can you count these points? Oh, you have these points also. No, you don't have these. You only have these ones. Fine. Okay, for people who have seen 11th grade chemistry, there's a thing called as off-bow principle or snake rule, something like that. You can try to relate it to this one to find an injective map. Very stupid example, but works.
You can take each diagonal starting from 1, comma 1.
Yeah. So you can basically like consider this diagonal first. So you count this. Then you consider this diagonal. So you count these two. And you say you start from left to right. So like this maps to 1, this maps to 2, 3, 4, 5, 6, 7, 8, 9. So on. You can do this. Now suppose I add all the integers. I add these stuff also here, these also, and these also. How will you still count them? Like you can still count them. I'm saying that z cross z is countable. Prove me how. The idea is same. Uh, Almost same. Actually, is it even same? No. Okay, probably not same, but you can still do it. As a hint, okay, if someone wants to tell me, I'll send you on private chat. I don't want to spoil it for everyone. Any idea? Oh, we are trying to find an like I'm saying that the set z cross z, which is basically all the lattice point in reals, is countable. So now tell me an injective map from uh, z cross z to naturals. That is how you prove countability, right? Okay, that is a good idea. Yes, that works. So someone said that when you count each point, you can also count it as flexion across x-axis, y-axis, and origin. So what you do is basically so suppose when you count 1 comma 1, you also count it as reflection across x-axis, which is 1 comma minus 1, and then you count this across y-axis minus 1 comma 1, and you count minus 1 comma 1, minus 1 comma minus 1, and then so this is 1 2 3 4, and then we count this. So now you count these elements also, and eventually you'll be able to count everything. But notice that you're not counting the numbers on the axis. You have to count those also. So how do you incorporate that? Like it's the same idea. In naturals, we're doing this diagonal thing, right? So now what you do is you take this diagonal first. So now you count the thing on the axis as well, and then this and this, and then you take this diagonal. So instead of counting just this thing, you count this and this and then this, and you keep on doing this. And you can just assign the number 0 comma 0 as the first element, and then you continue your counting. So is it clear how z cos z is countable? If you have doubt in any part, you can ask. I'll explain again. Come on, there are 6 people in class. Yes, no, anything. Okay, one person said yes. To others, if it's not clear, what part it is not clear. Okay, do you know what countable sets are and what are uncountable sets? The person who joined late. Can you please write the actual function for this, which would count them? Okay. Uh, okay, writing an actual function is. Can you write one second? Okay, I'll tell you a clever solution. Uh, like this works. So I'll first explain this side and then I'll give you how to write it explicitly. So what this idea is doing is, bias is not working. Hmm. You first count 0, comma 0. Then you count 0, comma 1. You go one step right, then one step down, like you're counting in this order. Then one more step down, then one step left. So basically, you're counting the square. So you count these elements. Now you count these elements. You go two steps above from 0, comma 0. Count this, count this, count this, count this, and so on. So eventually you count the square, and then you keep on counting all the squares. Do you see you can count all the z cross z elements? Now let's think of a clever map. Like, how do you write it in an exam? Suppose you have to write it in one line. Very stupid way to say. But anyway, suppose you have a comma b. So f of a comma b, we say, is equals to 2 to the power of 2 to the power a times 3 to the power b if a comma b are positive. 2 to the power a times 3 to the power b into 5 to the power into 5, let's say, if a is positive but b is negative, and 2 to the power a into 3 to the power b into 7 if b is positive but a is negative, and 2 to the power a times 3 to the power b times 5 times 7 if both are negative. Can you check if this function is injective? And this covers all the z cross z elements. Okay, for the person who joined late, I'll explain what countable and uncountable set means. Do you know what is an injective function? For other people uh, who know what stuff is going on, try to verify that this is a valid injection from z cross z to n, and hence this is countable. Like, see, nowhere in our set, so like there's no element x such that f of x is 11, right? But that doesn't matter. We are counting, so we skip 11 in our counting. Okay, so try to verify that this is an injection. Like, you just have to intuitively know that this is injection, and now try to find an injection from q to n. It's a similar sort of injection. Shouldn't be hard. Okay, for the other person, uh, do you know what is an injective function? Like, please answer yes or no so that I know. Okay, I assume we don't know. So a function f is said to be injective if uh, f of x equals to f of y is true if and only if x equals to y for all x comma y in the set A. So this is an injection. So now we say a set x is countable if there exists an injective function mapping the elements of x to natural numbers. So let's say you have the set of even numbers 2, 4, 6, 8, so on. We say that this is countable. We can find an injection from this set to the set of naturals. So one injection could just be f of x equals to x. So like this maps to 2, this maps to 4, this maps to 6, so on. This is a valid injection. Now the point of countable sets is you can count the elements, right? Like you can say that the element 2 comes first. So like what does comes first mean? Like f of 2 is the least number, and then 4 comes second in the list, 6 comes third in the list. So you can like write down all the numbers in an order. So that is what countability is. And the sets which are not countable is uncountable. So we were proving that z cross z is countable. And now the question is to prove q is countable, like set of all rationals. I hope it's clear. And everyone, is this clear that how is this a valid injective map? A yes or a no would be helpful by anyone. Okay, thank you. Oh, sorry, your yeah. Oh, oh, you were sending messages on private chat. That's why I couldn't see them on my phone. Sorry. People, if you send me private message, send on the other one. Like I'll send a hi from that one. If you send private message, send on this one because I'm checking chat from this. Yeah. Okay. Try to prove set of rationals is countable. Two raised to a negative power of. Sorry, I don't understand your question. Oh, two raised. No, no, we are not raising two by nat. Oh, sorry. Array, take this modulus here. That was the whole point of multiplying by 5 and 7. Is this now fine? Yeah, that's correct, Sanjana. Okay, one person found the map from Q to N. Uh, Anyone else? Any ideas? Okay. Sanjana, would you like to tell how you did it?
Okay, so all rationals can be written in the form P by Q, where P and Q are integers and Q is not zero. So you can
Yes.
just consider it as P comma Q instead of P by Q. So in that way, every rational is in Z cross Z, and we've already proven that that is countable. So rationals are countable.
Yep. Okay. So we'll state it more formally. So consider a map F1 from Q to Z cross Z such that F1 of P by Q is P comma Q. And now then you have a map F2 from Z cross Z to N. We just showed above, right? Because Z cross Z is countable. So now you can consider this function F, which is F2OO F1. I hope people are familiar with this notation. If not, then you can consider this just as F of P by Q is just like you first apply F1, then this goes to a Z cross Z element, and then you apply F2. And then now this goes to a unique natural. And this function F is basically mapping Q's to N. So is the map clear? And this shows that rationals are indeed countable. Okay, one person said yes, two people said yes. Other people, is this clear? Okay, another person said yes. Four people, five. Okay, good enough. Okay, let's see if we want to do something with. Okay, I'll say state a couple idea improving countability. So, like one idea is if you have to prove some set X is countable, you first find a map F from X to some another set Y, which you know is countable. So, like if you can find an injection from one set to another countable set, then your original set is also countable. That is what we did for Q, right? We know that Z cross Z was countable. So we mapped Q to Z cross Z. And then since this was countable, this is countable. This is one idea. Another idea is again, like just find a sorry. So another idea is basically how to find a nice mapping function. So like mapping some, let's say, tuple a1, a2, ak to p1 to the power a1, p2 to the power a2, where p1, p2, pk are first k primes. So until pk to the power ak is like a nice idea because see, you know that there are infinite primes and the primes are countable. So you can map everything to like some prime to the power that, like you have to find what that is, and this map will be always injective because like prime factorization is unique, basically fundamental theorem of algebra. So this is a nice map basically, like that's what this is the map we use for Z cross Z as well. Okay, so that was just a idea. Now let's see, shall we see a problem? Let me see. One second. Okay, let's do a problem first on this thing. Prove that we can't have an uncountable family disjoint disks in plane. Notice that the disks are disjoint and they're disks. So what is a disk? It's basically a circle which is filled. So like one disk has all these points inside it. So I have to prove like there can be some infinite disks on the plane, but but they cannot be uncountable. Like they have to be countable. So think about this for 5 minutes actually. Okay, not 5 minutes, 2 or 3 minutes. Like the idea is kind of new. Okay, I'll just tell you this. You have to do same thing. You have to find of like you have to show this is countable, right? So you have to show there exists a function f from disks to some set y where you know y is countable. Try to find such a function. Mm, Someone says a function that relates with the area of circle. Okay, think about it this way. If it was something with the area of circle, I could have just given you that there are disjoint circles instead of disks. So there must be some use of this. Like a circle is a subset of disk, right? But you cannot do that with circles. Like you can have uncountably many disjoint circles in the plane. Like I can okay, I cannot construct an example, but yeah, you can have uncountable. So area of circle is not the best thing. Scale so that there's at least many conditions. That is a very good idea and very close to the actual solution, except you cannot always do that. So let's say you fix some particular scaling, then you can show that like disks can be I can even take a disk of size 0.1 meter square. By size I just mean area, or 0.01 meter square. There is no bound on the area. So you can always pick a disk such that suppose these are 4 lattice points in a scaling. A disk is of some area this much, which is inside it. So that won't work, but you're very close to the solution. You're thinking of the right map. Uh, what other set you know which is countable? I'll tell the solution is 745, by the way. Okay, also if someone has any ideas, like feel free to speak your idea because they're actually helpful. Yeah, that is the correct idea. That works. Okay, so think about this. Suppose you have some disks in plane. I'll just denote them by circle, but assume they are disks. Some disk here, some disk here, some disk here. Now, notice that you can always find a rational point inside each disk, right? Suppose you pick this disk, then, oh, like, does everyone see that how we can find a point which is x comma y such that x and y both belongs to rationals? Like, if not, then see this. So, like, pick a particular line along this. This whole line is inside the disk. This line will obviously have some rational here. Like, this will determine the x coordinate, right? So you don't worry about the y coordinate for now, but pick some x coordinate which is rational. So now x is rational. And now vary along this line, your point. This is completely inside the disk, but this will have some point which is rational. So let's say this point. Now x was fixed and x is rational. So now x and y are both rational. So every disk must have a rational point inside them. Is this clear? Yes or no? Okay, other people. Sanjana, I know that you got that. Other people. Okay, yes. There are six more people in class. Yes or no? Four more. Counting is hard. Okay. So what I'm saying is also hi Pranav.
Hi.
Uh, suppose you have a disk, then you can find a point inside that disk x comma y such that both its coordinates are rational numbers. So that point is basically a rational point. Can you find such, like, do you see that there should always be a rational point inside a disk? Okay. I assume that's clear. So now what we do is you found a map F from disks to Q cross Q. Now we know that Q is countable. The set of rationals is countable, right? So how do I say this nicely? Like if Q is countable, then Q cross Q should be countable. Like that should be kind of intuitive. But let's find. Okay, try to prove this now. If Q is countable, then Q cross Q is countable. You can find an injective map for this. Okay, since we don't have that much time, I'll just quickly tell the map. It's not that hard to think. Like suppose Q cross Q would look like something like A by B comma C by D, right? So you can just map it like 2 to the power A into 3 to the power B into 5 to the power C into 7 to the power D. And if they are negative, you can add some other factors like 11, 13, so on, depending on the sign. So this is an injection. So is this clear? So now we have that there's an injection from disks to q cross q, and there's injection from q cross q to n. We just showed this injection. So there's an injection from disks to n directly, which means that there cannot be uncountably many disks in the plane. Okay. Let me know if this question is clear or if you have any doubts. Yes, no, anything. Okay, it's clear to one person. What about other people? Okay, I assume it's clear. Or if you have any doubt, feel free to speak up anyway. Okay, shall we prove uncountability? Okay, uh, now we prove, like, we have seen a lot of countable sets. So let's find a set which is like, let's prove some set is uncountable now. So prove that uh, set of all 0, 1 sequences is uncountable. So say that the sequences are infinite. Set of all infinite 0, 1 sequences is uncountable. So what is a 0, 1 sequence? Basically, like a bunch of zeros and ones in some order. So like 0, 0, 0, all zeros. This is a 0, 1 sequence. All ones is a 0, 1 sequence. Uh, 0, 1, 1, 0, 0, 1, stuff like this. You have to prove that all such sequences are uncountable. I'll give you 2 or 3 minutes to think about it, but I don't think if you have seen the idea before, it's that easy to come up with. So think about it for 2 or 3 minutes and then I'll tell.
So suppose it is countable. So then you
Okay.
can order them in the order of the naturals.
Oh,
And
one
then you
second. One second. One second.
like,
Suppose it's countable. Yeah, then.
so you have like an order.
Yeah, so basically there is
So
this some ordering. So like on the first position you have some this. On second position you have some 0, 1, 6. Like let's say in first position the sequence is all zeros. On second position you have some 1, 0, 0, 0. Third position you have 1, 0, 1, 0. Stuff like this. Okay,
then you take all the numbers on the diagonal and you take the complement. So if it's a 0, you write a 1. So that sequence won't have been in your original set because some term is different.
okay. Right. So what we do is we consider as another sequence, another 0, 1 sequence. So the ith element of that sequence is basically, let's say, like the first element will be, so you see the sequence on the first number. This is 0 0 0, right? So the first element is 0. So I say the first element of this is the other thing. So if it's 0, then it's 1. If it's 1, then it's 0. So it's 0, so this should be 1. Now you go to second sequence and see the second element. This is 0. So this should be 1. Now you see the third sequence and third element. This is 1, so this should be 0. And you define this sequence like this. So now since the number of sequences is countable and this is a valid 0 1 sequence, this should be at some kth position, right? For some k. So let's say this is at some kth position. Now, if you look at the sequence at the kth position, let's say you have some sequence, and at kth position of that sequence, we have 0. So by definition of this sequence, at kth position, this should have 1, right? But this sequence was originally at the kth position. So this is a contradiction. Similarly, if there was a 1 here, there should be 0, which means that this particular sequence is not there in your, what do you say, counting, right? It cannot come at any place, which means that this 0 1 sequence is uncountable because we found a contradiction. So is it clear? Like, how is this a contradiction? But just a second. Okay, one person said yes. What about other people? Is this clear? Like two people, no, Sanjana, obviously. Okay, I'll assume it's clear to other people as well. Anyway, let's now move on. Okay, so we saw that this is uncountable. So now prove that reals are uncountable. Uh, what you said is correct, but how does that prove that reals are uncountable? Uh, the person who said that less than the said number argument, like we say that rationals are countable, but suppose I give you any particular rational, there always exists a rational which is less than that rational, but they're still countable. And yeah, Sanjana, your argument is correct. Any ideas, anyone? Okay. Uh, Divide the number by 10 to the power a. What does that do? And we can do it infinitely many. Sure, you can do that in rationals as well, right? Like there is no issue. Like if x is a rational, x by 10 to the power a is also a rational. Yeah, I got that. But how does that prove that reals are uncountable? Like, okay, whatever you think of, I'll say this, whatever you think of an idea, try to think if this works in rationals as well. Because you're saying that you divide the number by 10 to the power a, and then you can do that infinitely many times, right? But you can do that as well in rationals because you have some rational x, then x by 10 is also a rational, but rationals are countable. So if you're making an argument along that lines, then reals are also countable, right? Okay. Anyway, so see this. So you consider the reals of the form 0 point. Let's say we have some reals, and these are basically a 0 1 sequence basically. So like let's say you have some real of the form 0.10000, 0.11001100, so on. So you can just take like 0 1 sequences after 0, and this set is a subset of reals. And we know that this set is uncountable because we just proved 0 1 sequences are uncountable. And a subset of reals is uncountable. So reals are also uncountable, right? So is this clear? Yes or no? Okay, nice. Just a second. Yeah, yeah. Hmm. So okay, this is clear. What else can we do now? This will take longer. Okay, let's do this question. Uh, let C be a second. Suppose you have some collection of circles in the plane called C. This is collection of circles such that for all A on the x-axis, there is a circle in C passing through A, and tangent to x-axis, obviously at A. So prove that C contains a pair of circles that intersect. Also, this will be the last question. Like there are quite a few questions left which I wanted to do. So if people are interested, I might take a part 2 as well, which will be shorter than this class, like 45 minutes to 1 hour. But anyway, let's do this question until then. Circles intersect tangentially, one positive and another is negative. Or uh no, like circle can, like you're just given that 1 second. You're just given this. So like for every point A on X, there exists some circle which is tangent to A. It can be in this direction as well, or it can be in this direction as well. But there should be exact at least one such circle of this form. Yeah. Is that, does that answer your question, by the way? Okay. So like the tangential thing can be in positive as well or negative as well. Doesn't matter. What you are given is for any point A on the x-axis, there exists some circle which is tangent to it. It can be here as well or here as well. That is fine. Anywhere it can be. Is that clear? Okay. Yeah. Okay. I didn't understand. Sorry. Okay. Also, feel free to speak any idea even if you're not done, because that will be helpful.
Okay, so every circle has a real number associated with it, right?
Yes.
So
A real number.
reals are uncountable, so that means the circles are uncountable, right?
Yes.
So we have proven that disjoint circles are countable.
That is disjoint discs, not circles. That's the issue.
Okay.
Oh, wait. You're saying disjoint circles. Oh, yeah. Yeah, fine.
Wouldn't that also be true?
Yeah. Same idea. Sorry. Yeah, so
Yeah.
that's correct. That's basically the idea. So what you say is you assume that no two circles intersect. So you have some bunch of disjoint circles, like, and disjoint circles you can basically assume as disjoint discs. Doesn't matter, right? And now we know that disjoint discs are countable. So we know that the set C is countable. Changing the radius will lead to pair of circles that are tangential and intersect. Sure, but how does that help again? Like, how do you show that there does exist circles which intersect? Like, you have to show. You cannot change a circle which exists in C. You have to show given any set C satisfying this property, there exist two circles which intersect. Okay. Anyway, so I'll continue this. So we got that C is countable. But now let's think of another way. Each circle is linked to a rational number, a real number A on the x-axis, to which is tangent, right? So there is a bijection, like every circle, like every real, there exists exactly one circle corresponding to that real. So now you can say that the set of circles is uncountable because reals are uncountable. So get C is uncountable. But both the things can't be true at the same time, right? So this is a contradiction. Anyways, the argument clear. I might have said something which might have confused anyway. Let me know if it's clear or not. That was the last question for the class. I'll give you an exercise before we end. You can think about it and message me asking if it's correct or not later. Okay, people, is this clear? Okay, one person said yes and Sanjana answered, so two people said yes. What about the other people? Okay, I assume that is clear to everyone. This is exercise which you can try later. Prove that countable union of countable sets is countable. Okay, what it basically means is, suppose, array, one second. Uh, yeah, suppose you have some set I of sets x1, x2, x3, so on. So basically, like these are countably many sets. Like there can be infinite sets, but I'm saying that they're countable number of sets, and each set is countable. So like each set has countably many elements. They can be infinite, but again countable. So now prove that x1 union x2 union x3 so on. This set is countable. So is the question clear to everyone? A set of intersecting disks is not countable. Yeah. If you have a set of intersecting disks in the plane, you can show it's not countable. You can basically find a map from that to reals or find such an example. Okay. So this is your homework question. Homework sounds schoolish. So I'll just say this is an exercise. You can message me on Discord, asking any hints or anything on this. If I do decide to take another part on this, because I have like 5 or 6 problems, so we can do that later. Then we'll start the next class from this exercise. We'll first prove this and then start. But yeah, that was it for this class. I'll stop recording and I'll stay here for 3 or 4 minutes if you have any doubts. Stop recording.